So let's start. We had started talking about isomers, and we were at this thing, stereoisomers. This is what we were doing. That there were molecules having the same molecular formula as well as the same structural formula, exactly the same connections, except that the orientation of the bonds in space, the three-dimensional shape in space, is going to be different. So this has a lot to do with the shape of a molecule. I gave you the example of your two hands. They kind of have the same connections, except that the direction of the fingers, etc., they're all different. So the first one was optical isomers, and I told you that they have chiral centers. That was one of the conditions for the formation of an optical isomer, that it's supposed to have chiral centers. Which is that the carbon atom should be making 4 single bonds with 4 different groups. So when the carbon atom is making 4 single bonds with 4 different groups, the molecule will have no symmetry. And which is why if you make a mirror image of the same molecule, just like your two hands are mirrored versions of each other, there's going to be another molecule which would kind of look exactly the same, except for the fact that it's going to be a mirrored version of it. So except for the fact that it's going to be a mirrored version of the same thing. Second. So it's going to be a mirrored version of the same thing. So so the bonds would all be pointing in different directions. So I've got this molecule which looks exactly the same. It's got an OH on the top. The CH3 is pointing this way. So the CH3 is pointing the opposite direction. The CH2, CH3 are pointing this way, and you've got a Cl over here. So the molecule looks, and there's an OH here. So the molecule looks kind of the same, except it's a mirrored version of the same molecule. So this one is going to be a mirrored version, just like your two hands. They kind of look the same, except that no matter how you rotate one of your hands, it's never going to have exactly like, even if you try to rotate your hands, I mean, if you correct the direction of the thumb, the direction of the palm would change. So the molecules would always, some of the bonds would point in different directions, no matter how you rotate one of them. Okay, just a second. So no matter how you rotate one of them, and just 1 second. As I said, no matter how you rotate one of them, the molecule would always look different. So can you all hear me properly? Hello?
Yes, sir.
Yes, sir.
Okay. Just 1 second. So the molecule would look different. So you're looking for a chiral center, always looking or searching for a chiral center in a molecule, and it's going to have mirrored versions. So there would be 2 different molecules. Now remember, the 2 molecules look the same, but they would have completely in biology. It's a severe issue. Okay, chirality is very important when it comes to biology. So chirality is extremely important in biology because everything is shape specific. Because in biology, even at the macro level, like if there's a glove and your right hand fits into it, your left hand would not be able to fit into it. So chemical reactions, especially biological reactions, are complicated molecules which have a certain shape. You've got the lock and key model. So in the lock and key model, if the molecule, so it's like a key. Okay, think of a lock. You're trying to insert a key into it. The key should have a specific shape. If the key is a mirrored version of it, the lock will not be able to accept it. It won't be able to fit with it. So if one molecule is working or acting as an enzyme or some sort of catalyst in a biological system, the other one would not be able to fit with it because its bonds would be pointing in opposite directions. The Cl is pointing left, over there the Cl is pointing on the right. So just think of a real lock and key model. If you have a mirrored version of the key will not fit into the lock and will not be able to react with it. So the same thing happens with these molecules. So one will work, the other one will not work. And this is a huge problem in medicine as well, because one will work, the other one probably causes side effects, which is why you have a lot of side effects in medicine. Because one of the molecule is working perfectly, it's helping you get rid of a particular virus or some bacteria, while the other one is not working and it's instead causing a lot of harm. It's reacting with other things. So that results in side effects. So one chiral molecule might work, while the other one would cause side effects. Would cause side effects. So natural systems are kind of, they don't usually have chirality. Like, for example, natural medicine that comes from natural, your herbs, etc., herbal medicine, they don't really have side effects because nature has kind of found a way of making just one of them. For example, we are made out of amino acids. Most amino acids are kind of chiral. But natural systems, they usually work with just one. In the lab, it's very hard to make only one. You usually end up with two of them that they look kind of exactly the same, except they're mirrored versions of each other. So synthetic molecules, a lot of chirality exists in synthetic molecules, but natural systems usually have found a way of making just the right one. If this is the right one, they're just going to make this one, not the other one. So anyways, you're looking for chiral molecules. So we're going to try and spot the first question that you're going to get is you're going to try and spot chirality in a molecule, and then we're going to draw the three-dimensional shape of the molecule, the mirrored versions. So for example, I've got this molecule over here. And there is CH3. This is CH2 with a Cl. You've got an H, you've got another H, and you've got 3 H's with this one. And you've got a Cl over here. Can you spot a chiral carbon atom in this? Anyone? Can anyone find a chiral carbon atom in this? The one that's bonded to 4 different groups. Single bonds and... So which one is chiral?
Second one.
Okay, second one from the right or left?
Left.
Okay, so the second one is chiral, this one. Because, and remember, when you're spotting if it's chiral or not, you have to look at the entire side. So on one side you got an H. On one side there is a Cl. On one side there is a CH3, and on the fourth side there's this entire thing that's connected to it. So it's got 4 completely different things that are bonded to it. And apart from this, so this one is chiral. This carbon atom would have 2 separate 3-dimensional versions. They would both be mirrored versions of each other. Can anyone spot any other chiral carbon atom apart from that? Apart from the second one, is there any other carbon atom that's chiral? TK, is there anyone, Zabe? Any idea?
The second carbon from the right.
Okay, so the second from the right is, so this one has two chiral carbon atoms because this one is also bonded to four different things. You've got a CH2Cl on one side, you've got a CH3 on one side. The third side is H, and the fourth side is this entire thing. So this one is also chiral. So that means this carbon atom has two chiral carbon atoms, the second from the left and the second one from the right as well. And so I'm going to draw the first one. I'm going to draw the three-dimensional representation of the first one. And 1 second. So I'm going to draw the three-dimensional version of the first one, this one. In the three-dimensional representation, you're going to have the carbon's actual shape would be tetrahedral. So you got a tetrahedral carbon atom. This one, that's the middle carbon atom. I'm not concerned about the shape of all the other molecules. I'm just going to show this one. So this one has, and you'll be asked questions like this. So you'll be asked to draw this. So this one has an H on the top, a CH3 that is on the left side. It's got a Cl that's at the bottom. And on the other side, it's got a CH. So on the right side, it's got a CH with a CH3 branch. And on the right, there's a CH2Cl as well. So this carbon atom is chiral. I'm going to draw a star with it. And it's going to have two different mirrored versions. So let me just copy this and I'll draw the other one as well. The molecule would exist. And it's going to have two different. So this one over here is going to have two different shapes. The other one would be a mirrored version of this. And that mirrored version would be this one. I mean, the H, everything has to be drawn the other way around now. Just like you trying to draw your two hands. So one of them is just a reflected version of the first one. So the other version of this molecule would be, it's going to have a CH, then there's going to be a CH3 branch, and then you're going to have CH2, and you're going to have Cl. And there's going to be a Cl over here. And there's going to be a CH3 on the right side. So you should learn how to draw. You'll be asked very frequently to draw the chiral carbon atom and the two different representation, two different structures that this molecule would exist in. So the bond directions would be different. This one will have different directions. This one will have different directions. So is this clear what a chiral carbon atom looks like and what is optical isomers? These two are optical isomers of each other. So is this clear?
Yes, sir.
Okay, everyone, is this clear? Mayim, is this clear?
Yes, sir.
So just look at chiral carbon atoms. Now this molecule, not only is this carbon going to exist in two different shapes, this other carbon atom would also exist in two different shapes. And I'm going to call them, one is usually referred to as the plus, the other one is usually referred to as the minus, like mirrored versions of each other. You're not able to identify this by just looking at the diagram. You can't really tell which one is the plus and which one is the minus. I'm going to talk about the differences between the two. How are you able to identify that? But you won't be able to identify it by just looking at it. But anyways, one of them is usually referred to as the plus, the other one is referred to as the minus one. So it's kind of like the two mirrored versions, okay? Just like your two hands, you call one of them your right hand, the other one your left hand, right? So the same case, there would be two different orientations. One would be called plus, the other one would be called minus. Now the question is, how many different stereoisomers would be possible in this case? Because in this case, you've got two carbon atoms and each one of them has two different orientations. I mean, this carbon atom could exist in the plus version and it could also exist in the minus version. The other one would also exist in the plus and the minus versions. So if you look at the entire molecule, so how many different stereoisomers are possible? So remember, if a molecule has two chiral carbon atoms, then both of them could be the plus versions, okay? Because this carbon will have two versions, this carbon would also have two different versions. So one molecule could be, I mean, if you look at the entire molecule, then you could have one molecule which will have the plus versions of both of them. You could have a molecule where the first one is plus, the second one is the minus version, or the first one is minus and the second one is plus, or there could be a fourth molecule where both of the carbon atoms are in their mirrored form. They could be the negative versions of each other. So if a molecule has two chiral carbon atoms, okay, just remember that each one of them, let me just move 1 second. So just remember that a chiral carbon atom would have two different shapes. So it could either be this shape or it could either be this shape. It could either be the plus version of the molecule or it could be the minus version of the molecule. Okay, so the molecule could, I mean, that particular carbon atom could have two different shapes. And if it has two different shapes, and since the molecule that we have over here has in total two chiral carbon atoms, so this one is doing the same, this one is doing the same. So this entire molecule could have four different versions. The three-dimensional shapes of this molecule, there could be four different three-dimensional shapes of the molecule. And that would result in four different stereoisomers. Did you get this point? This one, the last one. Is the last point clear?
Yes, sir.
Anyone else? I'm going to come back to this point. I'm going to talk about this in a lot more detail just in a bit. We'll do the other one and then we're going to talk about this. But for now, just remember that whenever there's a chiral carbon atom, around that carbon atom, the molecule is going to have two different shapes and they would be mirrored versions of each other. So I'm going to come to this last point later on, just after doing the other one. So this is what chirality is. This is what optical isomerism is. The orientation of the bonds is going to be different. I'm going to elaborate in a lot more detail the last point. Just after this one. After studying the second type of stereoisomers, and that second type of stereoisomers, that's known as, the second type is known as geometric isomers. They're referred to as geometric isomers. In geometric isomers, what happens is, first, the necessary conditions. Again, it's a type of stereoisomers, so the orientation of the bonds is going to be different. So in geometric isomers, the first condition is, which molecules would show geometric isomers? The first condition is that there must be carbon double bond carbons. They must be present. I mean, they've got to be present. And the second condition is that each carbon in C double bond C must be bonded to two different groups. So let's first try and understand what the conditions are. The condition states that a double bond is a must. So let's figure out which molecules, let's try and figure out or classify which of the molecules would be able to show geometric isomerism. Forget what geometric isomerism is, just let's try and figure out which molecules are going to fulfill the first two conditions. So I've got a molecule here, it's got a double bond. And and I'm going to add all the other atoms. So let's say there are hydrogen atoms. There's got an H, and this one is a carbon with 3 H's. Now the first condition is met. A double bond is present. But the second condition is not met. It says that each of the carbon atoms in the double bond must be bonded to two different groups. So look at this carbon atom over here, the first one on the right. It's not bonded to two different groups. Okay, so it's not bonded to two different groups. So that condition is not met. The other carbon atom is bonded to two different groups. So that condition is met over there. I mean, it's got two different groups. So each carbon atom must be bonded to two different groups in the double bond. Each carbon in the double bond. This one is bonded to two different groups. This other one is not bonded to two different groups. So on that side, the condition is not met. So this one will not show geometric isomers. Or will not make geometric isomers. So let's do the other one. Just hold on 1 second for the azan. I should say this one. So I'm going to search for geometric. Remember, we haven't studied what geometric isomers is. I'm just trying to figure out which molecule is fulfilling the conditions first. So this one, you've got a double bond. Okay, so that condition is met. The first one is correct. And then each carbon atom must be in the C double bond C must be bonded to two different groups. So look at the carbon over here on the right. This carbon atom is bonded to two different groups. It's got a CH3 and it's got an H on one side. So this carbon atom is fulfilling that condition. The other carbon atom must be bonded to two different groups as well. So it is also bonded to two different groups. So this one will make geometric isomers. The same is true for this one. This one is also meeting the conditions that there's a double bond present. And each of the carbon atom must be bonded to two different groups. So this carbon atom is bonded to an H and it's bonded to a Cl. So that's fine. And this other carbon atom in the double bond must be bonded to two different groups as well. So it's bonded to an H and a CH3 on one side. So this one is also fulfilling the condition. It's bonded to two different groups. So is this clear? Okay, which molecules will make geometric isomers? So is the conditions clear?
Yes, sir.
Okay, so Mariam, is this clear? Alicia, is this clear? Zahib?
Yes, sir.
Achha.
Yes, sir.
So that's the first thing. You have to know which ones would make geometric isomers. Now, what is geometric isomerism? Why do you need this? TK? What kind of isomerism is this? TK, so let's talk about that. Now, the thing with geometric isomerism is that you've got whenever carbon makes double bonds, TK, so you have to go a bit further back. Carbon is going to be sp2 hybridized. Because whenever carbon is bonded to or making a double bond, it's only bonded to three atoms. One over here, one over here, one on this side. So it's only bonded to three atoms. So when carbon is bonded to three atoms, it is fan-shaped. It's fan-shaped and it's going to be trigonal planar. Okay, that is what the carbon atom would kind of look like. 1 second. So it's going to be fan-shaped because it's only bonded to 3 atoms. So carbon has 4 electrons, but 3 of the electrons get pulled in different directions. One is being pulled by the hydrogen atom. The other one is, but let's talk about this one. One of them is being pulled by the carbon atom next door. That's the CH3 group. The other electron is being pulled by the hydrogen. Over here on the right side, you've got another carbon atom, and the same thing happens with that one as well. You've got so 1 second. So you've got this other carbon atom, which is exactly the same, this one over here. It's going to be bonded to an H and a CH3. So its electrons are being pulled by an H on one side and by a CH3 on the other side. So this one, all of them are fan-shaped. It's trigonal planar. I mean, each of the carbon atoms, like the ones that are making the double bonds, the ones I'm marking, they're going to be trigonal planar. And they would be making, so it's just like fans. You get 2 fans connected to each other. So the angles would be 120 degrees, all of them. It's going to be a flat planar molecule. That's one blade of the fan. That's another one. That's the third one. This one also, 3 blades of a fan. And the molecule cannot change shape because the 4th electron of carbon, which we hadn't shown, there's a spare 4th electron that would be in its p orbital. They would end up forming a pi bond above and below. Okay, so there's going to be pi bonding happening. Electron cloud would be above and below. So there's going to be this pi bond. Now you can't really twist this pi bond, but the molecule is locked in place. And so this is the double bond over here. So remember this sp2 hybridization, carbon atom is bonded to 3 things. The 4th electron of carbon is available. It says there's a spare 4th electron. So there's an electron that's buzzing above and below. The same happens with this carbon atom. You've got 3 normal bonds. The 4th electron of carbon is buzzing above and below. So they start overlapping above and below the planar molecule. And the molecule is locked in place. So what happens is that you can't twist this molecule around. So the molecule is going to maintain its shape. It's a very rigid shape. You can't change the shape. Just like the 3 blades of the fan, they're locked in place. The H is always pointing in this direction. The CH3 is always pointing. It's always on this blade, and this is the other carbon atom is on the left side. So there's going to exist another molecule which would have exactly the same connections, except that one of the sides would be different. The direction of the bonds would be different. For example, there's going to be another version of the molecule where the H, instead of pointing downwards in this direction, and the CH3 instead of pointing upwards, their positions are switched around. I mean, they're connected to the same atom. Okay, the connections haven't changed. They're connected to exactly the same atom. It's the same carbon atom that they're connected to, except for the direction of the bond. The direction of the bonds are different in this one. So the direction of the bonds are different. So I'm going to highlight that thing that's making them look different. So you had these H atoms. So the 2 fans were connected together, and both H atoms were pointing towards you, like or pointing downwards. Now you've got 2 fans connected to each other, but the only difference now is that the H atoms are pointing in opposite directions. And so the molecule connections are exactly the same. There's nothing wrong with the connections of the molecule. The H atom is still bonded to the same carbon atom. This H atom is still bonded to the same carbon atom, except for the fact that the H atoms are pointing in opposite direction. Over here, the H atoms are pointing in the same exact direction. So one of them is known as a cis isomer. Okay, both of them are exactly the same. The orientation of the bonds is different. One of them is the cis. Cis version is the one where the same group points on the same side. Or you can say same group is pointing, forget the pointing word. Same group, it's going to have the same side. And this one is your trans version. In the trans version, the same group, it points in opposite directions. So is this clear that you're going to have a cis version and a trans version, and the molecule would exist in two different forms? The connections would be identical, but the three-dimensional shape would be, I mean, they're going to look different. Okay, is this clear? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So, okay, so we're gonna do this. We're gonna try and find. I'm gonna try and make optical isomers of this one. Okay, this molecule over here. Okay, let's try and draw optical isomers of this one. I think we did. No, we didn't. Let's draw this one. Okay, so let's draw the optical isomers of this particular molecule, which is. Let me just copy this. Okay, it is meeting the conditions, so it's going to form cis and trans isomers. So this one, you've got a double bond. So remember, everything would happen or revolve around the double bond. Okay, around the double bond. So if you're asked to draw the cis and trans versions, everything revolves around the double bond. Around the double bond, remember the shape of the molecule is fan-shaped. So you got one bond over here, you got one bond over here. So the angles would be 120. They're going to be 120 degrees. So focus on the double bond and the shape around the double bond. It's fan-shaped. Okay, all the bonds would be like the blades of the fan. And once that is done, what needs to happen is that you would need to add in all the groups. So you can make the first one. I mean, this carbon atom on the right is bonded to an H and a Cl. So I'm going to add an H and I'm going to add a Cl. This other carbon atom on the left is bonded to an H, and so on one side it's bonded to an H, and on the other side it's bonded to a CH3. So that's one three-dimensional shape of the molecule. And this one is going to be known as the cis version because the same groups are pointing in the same direction. Look at the H atoms, they're pointing in the same direction. So this one is your cis version. And there's going to be another version of the same molecule. The three-dimensional shape is going to be different. The connections would be exactly the same, except that the bonds are going to be pointing in opposite directions. So we're going to draw the trans version now. All you have to do is you got a double bond, H and CH3 are bonded to it. So the carbon atoms, H and CH3 are bonded to it. And on this side, H and Cl are bonded, except that the H is no longer pointing upwards. The H is the one that's pointing downwards, and the Cl is the one that's pointing, it's pointing upwards. And the H is the one that's pointing downwards. So what has happened now is that previously your H atoms were both pointing in the same direction. Now your H atoms are kind of pointing in opposite direction. The connections are exactly the same. The H is still bonded to the same carbon atom. This H is also still bonded to the same carbon atom, except for the fact that the direction of the bond is different, and that's your trans version. Okay, so you've got a cis version, you've got a trans version. Is this clear?
Sir, I have a question.
Yes.
What if all of the groups bonded are different? How do we know? How will we know?
Then you wouldn't be able to know which one is cis and which one is trans. Okay, there's another naming system, which is known as it's known as I mean, it's a different naming system. Instead of calling them cis and trans, the concept is exactly the same. It's exactly the same, but that one is not in your course. For you, it's just cis and trans naming. So all 4 groups can be different and the conditions would still be met. I mean, all 4 groups can be different. The condition is that each carbon atom must be bonded to 2 different groups. So this carbon atom must be bonded to 2 different groups. This carbon atom must be bonded to 2 different groups. So all 4 can be different, but then you won't be using the cis-trans naming mechanism. You'll be using a different criteria. Is this clear?
Yes.
That one is not in your course. So let's do other. Now, there's another thing about this is that geometric isomerism is not possible in double bonds in cyclic structures. So they're not possible in double bonds, even though conditions are met in cyclic structures. So as an example, I've got a cyclic structure. It's got a double bond carbon atom. This carbon atom is bonded to 2 different things. There's a carbon chain on one side. This carbon atom is also bonded to 2 different things, and there's a carbon chain on the other side. As another thing is, it's meeting the conditions through 2 different groups, 2 different groups. You got a double bond. I've drawn the 3-dimensional shape. It's going to be fan shaped, and this is the cis version. But the thing is that it's cyclic. That the carbon chain goes around and joins with itself. So the conditions are met. The 2 sides are different. The 2 sides over here are different. The only thing with this is I can't make the other one. Like, it's impossible to make the trans version. I can't. I mean, there's not going to be another molecule where the H is pointing downwards and the carbon chain is upwards. I mean, you would have to break the carbon chain and connect it towards the top. That would be kind of impossible. You can't switch it. Like, the carbon chain is cyclic. So remember, when you're making cis trans, you're not actually breaking any bonds. The only thing is there are 2 different versions of the molecule. The direction of the bond is different. The H is pointing downwards, the H is pointing upwards. You didn't break the bond. It's still connected to the same carbon atom. Because if you break the bond, if you change the connections completely, that's a structural isomer, not a stereoisomer. So over here, you can't change the orientation of the H atom, because then you can't bring the carbon chain and connect it to the top, because you would have to break this carbon chain, and only then would the carbons get connected to the top. So cannot change the sides over here, as the carbon chain has to be broken. Would have to be broken. And then that would not be a stereoisomer. Then that would be a structural isomer, not a stereoisomer. In stereoisomer, only the direction of the bonds are different. That's it. Okay, so is this clear that, I mean, it would be impossible to make a trans isomer of this one. Okay, it would be impossible that there's a trans version of this existing. Is this clear?
Yes, sir.
Okay, everyone else, is this clear?
Yes, sir.
So just ignore double bonds in cyclic structures. They're not, I mean, they would only exist in one version. Most of the time, it's just the cis version. Can't really change this side. Okay. So I said, now we're going to talk about, but we're running out of time. Okay. We're going to talk about in the next class, we're going to talk about the thing that we talked about. If a molecule has multiple, what happens if a molecule has multiple chiral carbons if it's a chiral carbon, then there would be mirror versions of each other. Okay, so there would be two molecules that would look exactly the same, but they would be mirrored versions. So if a molecule has multiple chiral carbon atoms or it has multiple double bonds which are making geometric isomers. Making geometric isomers. So let's talk about this in the next class then. Okay, we'll do past paper questions related to isomerism. So okay, everyone, take care. Allah Hafiz.
Thank you. Allah
Allah Hafiz.